everyone, thanks for joining today. I made this video just to talk about time series analysis. Basically, I'm just going to go through kind of what a lot of really smart people have done in statistics and machine learning, kind of get up to date on what are some ways to look at time series. So in order to do this, I'm actually going to look at a couple different papers. Here's the first paper, which I highly recommend you check out. A highly comparative time series analysis, the empirical structure of time series and our methods. And it's just a really good overall paper and kind of really explicitly focused on understanding all these methods that we've used to look at time series data. So first, we could talk about what is time series, and the fact is it's a very ubiquitous sort of concept in finance and medicine, biology, meteorology, and all sorts of different fields. But the idea is, you just have some data, some repeated measurement over time. And so this idea that you have some time, so this can be like a stock price, this can be like an EEG, some space recordings, meteorology, even random numbers. All of these sort of aspects have this sort of time series approach to them. And again, they're in a lot of different fields. You can even think about things like text or language as being a time series. A video is a time series of images. So you think about really, time series, this can be applied very broadly and can be very interesting to think about your sort of data in this time series frame. So this is from the paper, and I'm not going to go too much into this, but basically this paper was really kind of interested in identifying, what kinds of time series, what does it mean to do some kind of time series method, and how can you compare that across another time series method. I highly recommend you go check that out. But essentially, at the end of the day, I think the big sort of takeaway is that there are sort of differences, and this is kind of a graph that just kind of illustrates, the differences between different sort of time series methods and how they're fundamentally different. When you think about doing a time series method, it's actually really important. It becomes really important what you're actually doing and how that relates to your actual data. And so this is just going to go into more of like what are some of the ways that they're talking about in this paper, or which is really what are a lot of the ways that we have thought about looking at time series data for a large amount of their history. And so I think a lot of people might be familiar with the idea, or at least at first guess, if you haven't really done too much time series analysis, you might do something like, okay, well, let's just look at the distribution. And so this can be things like what is the standard deviation of the effect every single time step. What's the size of that effect essentially? What's the mean expected value? Is there a drift upwards? Is there a drift downwards? Is there no drift at all? And this sort of equates back to, if you're familiar with the finance concept of risk return. And so those are the return being the mean and the risk being the standard deviation. You're essentially saying of a stock price, you want to understand the time series of that, the time expectation of that as it moves forward. In terms of the basic standard statistics of the distribution of that time series. You can also check things like Gaussianity, saying if these processes are Gaussian, grow from Gaussian processes or not. And so these are sort of interesting ways that you could actually look at it, but you could also go a little bit deeper. And so if you have done a little bit of time series data, you might be a little bit more familiar with this concept of autocorrelation. And you'll see this word auto a lot when we talk about time series, essentially just referring to self. And so autocorrelation just is a self-correlation. There's a lot of math, but essentially, if you just have any, a time series of any time, right? So you have something like this. You see that there is some sort of seasonality effect. And essentially, if we know, what happens in this region, we might be able to predict what kind of movement would happen in this region a little bit easier. And so this idea that, using past information, and so this is this I minus I plus K, that would be like the K time steps ahead. It's like, can you predict K time steps ahead, based on the lag? And so you're basically, and essentially, you can do this a lot of ways. So I said predict, that was actually for a regression model. Since we're just checking the correlation, we're literally seeing, what's the correlation of time I plus K to correlation of time I for every single I in here. And if you have a really high I correlation, especially if you have like a lag of 1, then that would just mean that, the previous value, the value is highly correlated to the value you just had, essentially. And this is true for a lot of things like stocks. But you can also see you get this on a time value that's more than 1 when you have, long-ranging effects. So this is like things like seasonality. You're able to, and maybe every year you'll have some recurring effects. So this time period will be 365 days or however your years. And very similar to that is this, power spectrum. You sometimes see this. This is just a Fourier transform of the autocorrelation. So it's just a very similar sort of method to using the autocorrelation. I'm not going to go too much in detail, but just know that it kind of comes from the same sort of approach. So next, when you talk about stationarity, this is this idea in time series that essentially the properties of your time series may not actually be consistent over time. And so, like, if you have something that will keep going up, essentially a drift, then you'll have a non-stationarity effect because the mean of that time series will be different at 2 years from now than it is today if it's constantly going up or down. And so there's some different ways you can actually deal with stationarity. So you can do some kind of pre-processing essentially, and you're just gonna subtract the differencing. So it's just called differencing. You just subtract the lag point, and the idea of that is that you'll kind of subtract that mean. It's like there's a mean effect, a mean drift. If you subtract previous points from your time point and then look at that time series essentially, then you'll be able to actually get a uniform, mean. The mean should be the same because you're subtracting across at every time point. And then you could also, you could fit the residual, so you could fit another model, and we'll actually go to, there is a paper, one of the papers I'm going to go with you at the end, that actually does do this. So they essentially fit it with one of these, maybe like an auto-regressive model or something like that, and then you actually fit the residuals. Or you can, just do a feature transform, comment if some of your data is negative and some of your data is positive, you could just like add a constant to make sure everything is going to stay positive, and that'll help deal with some of these factors that if you don't actually do these things, it can actually mess up your data. And so next we're going to go into like a little bit of a different approach. And so this kind of gets more into the fact that, there's a lot of different sort of similar ways that people have thought about time series, but there's also kind of different ways. So thinking from like an information theory or entropic perspective, there's this aspect called auto-mutual information. This is a nice little review that goes into it. But essentially, if you have two time series processes x and y, or really any processes at all, your information about the process of x given y, and otherwise what's the information of y given x, can be given by essentially the probabilities, and this is actually very similar to the entropy formula if you're familiar with it. And so essentially, again, knowing x, how much do we know about y? Knowing y, how much do we know about x? You can actually kind of reframe this in a very sort of intuitive way, and now we're looking at the auto mutual information. So essentially, knowing t point, knowing this lag of t, we're able to actually identify, comparing x of t and x of t plus t, we're actually able to identify what is the information that we gain on this x process, knowing previous iterations or future expectations of this x process. And so that's able to actually get us a really nice sort of mutual information theory perspective. And here, there's also other sort of information theory entropic perspectives. And so if you think about, this is another, sort of approximate entropy. If you have sort of a time series of 0, 1, 0, 0, 0, 1, 0, 1, it goes on for 10,000 times, it's a lot easier to communicate that, and that's a lot more regular is what they call it, regularity. If that's what's called a regular time series, because it's easy to just say that there's not. I could just give you the information to recreate this time series very easily. I could just say 1, 1, 0 or 0, 1, say that 10,000 times. But if I just have a more or less random process, even though that these might have the same mean, these might have the same standard deviation, these are, you can see that the one of them is random, this one's kind of more ordered. And so the idea is really, from the entropic perspective, this information theory, can we actually compress this information in a way that we can actually understand this time series? And that's sort of the basis behind approximate entropy measures, is sort of really detecting this regularity effect. And so, again, these are just different ways you can really look at the time series. How do you want to look at it? Do you want to look at it in terms of the mean? Do you want to look at it in terms of the regularity? And it really depends on your specific end goal. And I think that this paper actually goes into that pretty well. So just talking a little bit more about, more complex, or I guess, nonlinear time series methods. And the idea essentially is the same, or is very similar to what we had been looking at previously. It's just we want to look at or classify these categories of time series with a few numbers. So they have this thing called correlation dimension, and these things called surrogate data analysis. And basically, these are just ways, like surrogate data analysis essentially just is similar to a bootstrapping, and you're essentially bootstrapping your estimates based on a linear model, and you're pretty much comparing based on if this null hypothesis, this linear model, this ARIMA fit was true, and if this ARIMA fit was not true, you can reject that hypothesis. And so these are just other ways, and there's sort of, it kind of gets I guess a little bit more complex into things like chaos theory and fractal dimensionality. And essentially, but these ideas essentially the same. So we have these small number of we want to have a small number to really represent this very complex process and differentiate. Like, for example, if I have an EEG from one kind of patients that I would consider healthy and another EEG from another kind of patient I consider unhealthy, or maybe a stock that might be a good stock or might be overpriced stock. And so you can actually, you want to figure out a way to compare those pretty easily using this really complex nonlinear representation. You can kind of use those to compare across, two different similar time series, figure out what kind of fundamental features will actually give you differences, or what kind of fundamental features can you actually recognize. And so this is sort of similar to what we just talked about. And so you can also use goodness of fits to a lot of these linear models. And so like this GARSH or ARSH process, which is a generalized autoregressive conditional heteroscedastic model. And basically it's just ways that, you fit models based on autoregression moving average. I'm going to go into a little bit more of these in a second. But the idea is essentially, compared to this ideal time series, this ideal linear time series, how does our time series hold up? Does this ideal time series actually, match the data that we have? And so these are important things that you can think about when you're actually looking at your own time series. And there's a lot of other different time series methods, and I'm not going to go into detail. Like a wavelet, which is just like, a small little thing of time series. You can look at the network property of these big time series, but it really depends on the field. I think there's a lot of different fields based on if you're interested in medicine or finance or whatever, a lot of different fields that can get, really interesting information on time series and have done really their own studies. So next I'm going to talk a little bit more about specifically machine learning and deep learning approaches in finance. But first I guess I'll go over a little bit more into this kind of paper. So when you look at the results of this paper, essentially what they're trying to say is essentially that there's a lot of different methods of time series, and there's sort of correlations between some of these ways. So this is a approximate entropy. We see that approximate entropy is kind of close to a lot of these other measures of entropy, and essentially these fundamental time series, and they talk more about like this stochastic sign map target, which is just another method, but it actually matches a lot of the data that we see in sort of real world meteorology and wind speed and stuff like that predictions. And so that there's basically what this paper was trying to say is that there's these kind of fundamental sort of time series methods, and there's essentially a lot of time series methods have been proposed that actually match up with different real world targets. And I think that it's really important when I looked at this to really make sure you're doing kind of a lot of different time series sort of analysis. And so this paper was really focused on a lot of the sort of statistics approaches, and I wanted to talk also about this machine learning approaches. And there's a couple of different very important distinctions. So like one of the reasons, I thought that was actually a very good paper that I just kind of went over, but they didn't really go too much into the sort of machine learning or deep learning approaches, and I think that they're just like fundamentally different. So the previous paper before had like a bunch of different time series methods, and that they created this code to kind of do all of these very historically studied and a lot of very diverse methods. But when you do sort of a machine learning approach, it takes a lot of time. It takes a lot more time to create a machine learning model than it does to create an ARIMA model or something. And that comes from optimizing your network and also actually training your network. Furthermore, these machine learning approaches usually tend to have a lot more parameters, and so it's a lot easier to overfit. So traditionally, you actually, well, at least in my impression, I think some people might disagree with this, but essentially, like historically, you usually get it's much easier to overfit, and it's much more difficult to make a really good machine learning model to look at a time series if you don't have that much data, because you risk overfitting, because these models tend to be so large. Like a big neural network will be so big, it'll essentially just memorize the data. And the other thing that these approaches kind of lack in general is this sort of interpretability. This is sort of kind of more intuitive to understand the sort of statistical approaches, and many times are kind of based on this really sound theoretical principles. But the machine learning principles, the machine learning approaches really aren't as interpretable when it comes down to it. So next I'm going to talk about this paper that's using multivariate long short-term memory neural networks with fully connected convolutional networks for time series classification. And so I think that this is more or less the reason I'm talking about this paper is more or less kind of the state of the art of a lot of different time series classification tasks. And so I think that this kind of is a good entry point, at least as right now it's October 2020, to actually think about how machine learning approaches have been really thinking about these time series problems. So this is just going to be a brief review, and this might be a little bit basic if you are familiar with neural networks and convolutional neural networks specifically. This might be a little bit more advanced if you are not as familiar with those. Just try to keep kind of, and I'll try to kind of talk to both fields really. But the idea of essentially the convolutional neural network is essentially this idea that was inspired by the brain. And this idea is that you essentially, when you look at something like an image, you go through different layers, and your receptive field gets larger and larger, and essentially you see different parts of your brain as the information flows through starts to see bigger and bigger parts of the image and starts to kind of combine them together. So you start again with just like with a bunch of small small scale interpretation of an image where you have just a bunch of little points, and then as you roll out and you go through your visual cortex, you're actually able to get larger and larger visual fields. Actually, at one point, you'll actually see the entire, or look at the entire receptive field. And so this is actually very similar to the way that convolutional neural networks work. So this is from the AlexNet paper. It's a very famous neural network. And I think it's a good approach. So given an image of size 3, so you have an RGB image, and you have a filter of size 11, you essentially are going to slide this size 11 by 11 across this image, and you essentially condense that information from each time you slide it by into a point, and then you do that 48 times across the whole image to get each channel. And then you do that again with another 5x5 filter. And the idea is essentially you have these different what are called channels, and each channel will look at the whole image, will scan the whole image in one way. And the reason I'm kind of bringing this up essentially is because one of the really important things about this paper specifically is that they introduced what's called the squeeze and excite mechanism. So this is how we had been doing it for a while, where essentially we just treated these channels as being completely independent. But now when we actually are going to introduce what this method is looking at, we're going to show that they actually control for the channel-wise statistics. They're actually controlling for all the channels in each layer instead of just treating them as independent. And so next, I'm going to go into a little bit more into long short-term memory neural network, or LSTM. And so these networks are actually kind of notoriously difficult to teach. And I think it took a while and a lot of different, number crunching, kind of thinking about it before I really started to get a better hang of it. But I think the idea I liked, at least the way that I kind of understood it best, was looking at sort of the math. So you essentially have this neural network, and it's based on a time series. So you need to have a time series to do this LSTM, or you need to actually, just at least represent your data as being a time series. And so essentially what you have is you have an output gate, you have a cell gate, you have a forget gate, and you have an input gate. And the idea is essentially every single time you feed in a sentence like science is great, writing is something else. So you say science, you feed in, that becomes the input. And then the gate itself, there's this function, this big function, which kind of goes through every time you feed it for a word, excuse me. And so you'll have a function. Just think about it in these sort of terms. You'll have a function that remembers what happened before, and that was the forget gate. And it's essentially it's telling the network how much to remember, or how much to forget, and there's another word to think about it, from the previous information. You have an input, which is what the input, this current word that you're looking at. You have the cell state, which combines the input and the forget gate from the previous time point. You can actually see this in the sort of the math right here. Is from the M time step, the previous time steps, and the forget gate, and you multiply the input gate times the cell gate. So you input, you have the input gate, you multiply that by the cell gate, and then you also have a function that represents the previous states. And then you have a function that represents how to output that, essentially. And so if you think about it, just again, think about it in terms of having an input, an output, a forget, and a cell. And going through, when you go through like a sentence or any kind of time series, essentially, you're able to actually go through those methods and able to remember what you did previously. And it's actually really elegant if you kind of know about neural networks. This whole thing is differentiable, and you can backpropagate through all that. So it's all nice and fun. You can train those pretty easily. So that's just a kind of more basic overview of LSTMs. And so this is really the, I think, a very important figure. This is the figure that they actually introduced in the paper. And essentially, I think it's a really elegant method. I really just want to kind of go through this. So having the input, they actually just take the whole input and they kind of go through it two different ways. The first is essentially they just have a convolutional layer on the whole thing. And they essentially, so when you look at the convolution, you can do a convolutional layer on an image, or you can just do it on a text, right? You just look at the whole piece of text at once. And then you have your window that goes through each string of that text, or each character of that text. And you're able to actually identify, that's how you get your different channels. And you actually do this squeeze and excite block, which we'll talk more about in a second, that actually models individual channel dependencies. And on the other side, you have a dimension shuffle, which I'll also go in a second. And then just really, you could just do a basic LSTM and essentially have a layer. And then you just combine your convolutional with your squeeze and excite blocks and your basic LSTM or your attention LSTM, and you actually get that into a classifier. And this is, again, it's actually kind of a little bit simple when you think about it, but this is essentially the state-of-the-art, one of the state-of-the-art models for doing time series classification. And so to talk a little bit more about this dimension shuffle, it's actually pretty interesting. So essentially they kind of flip it. So instead of looking at, assuming that you have m variables and q time steps, instead of using those q time steps, they're actually using m time steps, and they're going to treat it like there's q variables. But it's actually it's a very subtle distinction. They're essentially like pivoting the table almost. But they're able to actually retain the global information for all m's simultaneously, which is really interesting. And actually turns out to be a little bit more efficient when your m is smaller than your q, which is usually the case because usually you have a large number of time steps and a small number of variables. And so now I'm just going to briefly talk about this squeeze and excitation block, which is kind of a little bit new thing, which I think is really interesting. So this is from the original squeeze and excite paper. And so as we've said before, when you had a convolutional layer before, you had C prime channels, and you would just complete these channels as being completely independent. Well, what they do is they essentially say, well, we can just do these, computationally cheap methods to just kind of squeeze that down into a single vector and then model the dependencies of those vectors of that channel. And then we can kind of apply that back and actually get very interesting results that actually, they really just explicitly model. They say they use a global average pool to generate channel-wise statistics to actually, better incorporate these channels together. So you're actually modeling that these channels are not independent anymore, and you're modeling them in a certain way that helps you train better. So it's actually very useful. This is another example from the original squeeze excite paper. And so this is, if you think about it, you can apply this squeeze and excite block to kind of any sort of neural network or any kind of, I guess honestly, like any kind of neural network, right? But you can, so instead of just applying a residual network to a previous point that you had and doing this sort of skip connection or whatever, you can actually do the same sort of thing. But with your residual block, you can actually have the squeeze and excite block, which actually doesn't add too much computation, but does end up making it easier to train and a little bit more accurate. So again, this is just sort of the overall picture, the whole thing, and it's just very interesting. We essentially take into account the whole data set at once, and we use that in a couple different ways to actually generate our result at the end. It's very interesting. So yeah, these are just some results. I'm not going to go too much into detail, but they have pretty good results on their data sets, and you just know that they have things like EEG, food classification, gesture recognition, robot failure recognition, handwriting classification, so a lot of different kinds of tasks. So finally, I'm just going to talk a little bit more about this specific paper, which looked at high-frequency financial forecasting based on ARIMA models on deep learning. So this is kind of, to me, represented sort of an intersection between the sort of statistics approach and the machine learning approach. And so we're just going to talk a little bit more about ARIMA or ARMA modeling. And so it stands for autoregressive moving average. Essentially, if you just, again, look at the kind of the name, you have some formula, you have some x, which depends on the previous time points of I, t minus I. And so you add some time points, some previous time points, and some function with some formula to get the current time. Essentially, you're just saying that that time point depends on some previous time points. And you also have this sort of moving average, which is another sort of, you can think about how you can incorporate an autoregressive and a moving average. You also have an integrated moving average. But you see, these is just the formula here. And so the reason why we want to actually integrate this is essentially we're accounting for non-stationarity. Remember that essentially is just saying we want to make sure that the same sort of properties occur at time t versus time 1. And so if we difference these like if we have a duration of the season, we can just essentially subtract this to get the new value of the season. And we can actually, the ARIMA model kind of incorporates this sort of seasonality or stationary effect while also keeping these autoregressive and moving average. So the P would be how many lags you are behind. So if you have like, you can either say P is 1, which means it only depends on the previous time point, or P is 2, which means it depends on the previous time point and 2 time points ago. And the same thing with moving average. These can all be independent. You can have different DPs and Qs, and you usually find those as part of your model forecasting. So next I'm going to talk just a little bit about high frequency trading. And so this is the idea that, you know, kind of recently with the way that trading works and the way that equities are kind of traded, they're all pretty much traded by a lot of them are traded by algorithms or at very fast intervals. They're held for a small amount of time, and this sort of idea of fast, rapid trading with you know, a lot of very quick information makes up this world of, you know, high frequency trading. And so when I talk about, you know, how do we actually think about the statistics of looking at things like stock markets and models, we need to really think about sort of arbitrage-based pricing and sort of like, I guess, risk-free rate and alternatives. So basically this idea is that you can represent any kind of security or any kind of price as a function of other available securities. And if you find that some, you know, thing is not actually priced the way it is, you can actually just, it's pretty much free money or arbitrage. And so this is just a quick example. I'm not going to go too much into detail, but basically if you have, you know, a call option, which is essentially the right to buy a stock at a certain price, and you also have a short option, which is the right to sell a stock at a certain price. And you also have a forward contract, which is the contract you actually have to buy to buy or sell this at some price at some time. But the idea essentially is, you know, with these kind of commonly available instruments, we're able to actually identify that a portfolio must equal, you know, the call plus the risk, the call plus a bond, and a put plus a long forward must actually equal each other. And if they don't, there's actually free money in the market. You can just buy one side of this and sell the other side. And so where this actually comes important is when we look about how to actually, you know, price stocks. And so, you know, this common saying stocks only go up, which is actually not true. They actually do not always go up. But the idea is that you essentially have this drift rate that essentially relies on the risk-free rate. If I can go and get money from the U.S. Treasury bill or U.S. Treasury or the London Interbank, I can actually get, you know, an increase in value. So that basically this is reflected in the stock price, and you see a disproportionate amount of returns above 1 that wouldn't happen if this was normally distributed. So essentially, you know, the stock prices will always go up, and what they say in this paper specifically, these are all figures from this paper, and this equations from this paper, is essentially that you get a realistic fat tail distribution, which is more of how you know, financial returns actually work. And so this is all simulated data based essentially on the sort of arbitrage-based pricing or synthetic portfolio pricing that we had just talked about. And so that was one of the ways that they actually used to look and train their models. So this is from the simulated data, and they're able to actually show that when they actually do this strategy of fitting an ARIMA model and then looking at the residuals, remember this is actually one of the things we did already talk about, but essentially they fit this ARIMA model, which didn't actually fit out so good because you see the index in blue. The ARIMA models are kind of very predictable. There's not very much variance in them, so they generally will kind of stay close to the mean, and that's what we see here. But when we actually take the residuals and we actually try to fit them using an LSTM and an SVM, the SVM doesn't seem to work very well, but the LSTM actually seems to follow the initial data better. Although I think this figure is kind of worrying me because it seems like these are just discovering the lags afterwards, just the time period lag, which isn't really that helpful for forecasting because you're essentially just learning. It's essentially just overfitting or backtesting over the data and learning over that. They have pretty much shown that their LSTM was the best model. But I think this is really important. This kind of goes back to what we were talking about earlier in terms of the time differences. So in order to find, you do an ARIMA model to find the best P value, the D value, and the Q value, it takes around 14 seconds. But if you want to train an LSTM, it takes around 2,482 seconds. And so this is, again, why that other first paper didn't really look at the machine learning sort of methodology, because it just takes so much longer. And yeah, so they did this also on the Chinese stock index, Chinese securities index data, using high frequency data. They fit the residuals using an LSTM model, and they were able to show that it was actually better than the ARIMA alone or the SPM. But I'm a little skeptical of these results. I'm kind of curious. You see that there's these lags here. It seems as if really the initial data is just predicting the LSTM beforehand. I'm very skeptical. I'm not sure how much this would work. And I think that this kind of gets back into the really big about financial time series forecasting specifically. It has this element of backtesting or overfitting. Essentially, if you're testing on the same thing that you train on, and even if like you let's say you go back in time, you pick 200 stocks and you split it in half, and you train one model on the 100 stocks and you don't train on the others, like the macroeconomic factors in that same time period are going to have, or the systemic risk is going to be, intrinsic to those sort of models, and you're still going to learn that, and it's still going to be kind of very, very biased, right? Another really, I think, important thing that's kind of overlooked in sort of financial time series forecasting is survivorship bias. And so when you look at survivorship bias, essentially you're saying that, like, a company that's survived, when you're looking at the stock returns of a company from 5 years ago, that company had to have survived 5 years to get to that point, right? And so if it didn't survive, you wouldn't be looking at the data. And essentially that means that you're only looking at the successful companies. And when you're actually looking to apply that to new companies, to new time series, it's really difficult to actually, take into account that, you're only, if you're looking at data, you're only looking at data from companies that are still, working, or companies that are still in business, essentially. And finally, I think feature selection is kind of an important thing in time series. Forecasting is really important to understand, what exactly you're looking at in terms of, and how to represent that to a deep learning sort of algorithm. And so there's things like factor analysis, and sort of like, you can do things like ratio analysis and stuff like that for finance. But I think that it's really kind of difficult to learn these very sort of noisy and maybe not well-defined terms. And because what you're really given is like a stock price, right? And then maybe you have 5-second intervals, and a lot of that is kind of random. And so how do you actually represent that price? And how do you actually determine the best price in the future? And so these are just kind of things to think about. Hope you enjoyed just a little bit, learning a little bit about time series. Yeah, thank you. Appreciate it. Thanks so much for checking it out. Really appreciate you all sticking around for the video. You can definitely smash that like button and hit that subscribe button. It really helps me out, helps the channel out, help me give you more videos. Feel free to comment anything else you want me to go over. Thanks again. Really appreciate you.